seems it's working. Okay.
And I think everybody's getting the email.
Yeah. Now, just now. Okay, I think we can start. Okay. So, hi everyone, and welcome to this new webinar. As you know, this webinar is about eigenvalue analysis and response spectrum analysis in OpenSees. So let me share my screen. Here we are. Okay, so probably, as you know, eigenvalue analysis, of course, is already included in OpenSees. Response spectrum analysis is not. Here we just finished and tested the implementation of the response spectrum analysis directly inside the OpenSees code, and it will be available soon. Just tomorrow, we are going to send this code to the OpenSees maintainers. Then, of course, it will take some days, probably a couple of weeks, for them to include it in the new OpenSees version. Here I've written Eigenvalue Response Spectrum Analysis Part 1, because of course now you will see basically we have the first implementation of the response spectrum, and to do a complete response spectrum analysis with all the load combinations can be done, but will be available in version 2 of STKO that will be released by the first week of January. Of course, now we'll show you how it will look like with the new version. I will show you the developer version of STKO, and I will give you a brief introduction of the new features that you will find with STKO version 2. Okay, so this is what we are going to see today. So the new workflow for doing a response spectrum analysis in OpenSees is, of course, to use an eigen command to compute eigenvalues and eigenvectors, as you have always done now with OpenSees. Now, of course, the eigen command is just useful to get the eigenvalues and the eigenvectors, but of course, it doesn't give you anything more than that. So at most, you can know what are the frequencies, periods, and the eigenvectors. You don't have any information about the modal properties of your model. And when I talk about modal properties, I talk about the generalized mass matrix, modal participation factors, the modal participation masses, and so on, which is basically an output given by most of the softwares, probably all of them. And of course, you need all these things to understand how your structure is behaving from the modal point of view. And of course, it is mandatory for running a response spectrum analysis. So what we did actually is to implement two commands, okay? The modal properties command and the response spectrum command, okay? Now, when you use any other software, and for the sake of this tutorial, I will compare the result given by OpenSees with our implementation with another commercial software, which is Midas Gen, okay? So you can do a comparison. Typically, when you do a response spectrum analysis, you also do the so-called modal combination. Okay, so the output of the response spectrum analysis is already the modal combinations for displacements and all the internal forces and so on. Now we decided to do things slightly different. In our case, the response spectrum in OpenSees will just compute the modal results for each mode. Then the modal combination will be done in post-processing, and I will show you how, of course. Now, don't worry, because doing the modal combination can be quite tedious if you want to do it manually, but I will show you that in the new STKO version, this can be done very easily. And we are working on a complete wizard that does it for you, okay? The real advantage is that since we don't do the model combination before, you are not limited to a certain number of results, but you can combine any kind of result that you want, okay? So you have maximum freedom that you want with your outputs. Okay, so when you will run the model, you know everything about the eigenvalue analysis. I will give you some extra details about how to run an eigenvalue analysis and how to make sure that all the inputs are correct, what are the possible errors for an eigenvalue analysis. And then I will introduce you our new two commands, modal properties and response spectrum. Now, the modal properties is basically what we need to compute actually all the modal properties of our system. Basically, it will generate an output. Just a second. Okay. Okay, I'm having a little delay. Okay, if you give me a second, I will move to another computer because here we are having connection issues. Oh, now it seems fine. Okay. When you run the modal properties command, what you will have is basically an output text file, which is formatted in a certain way. It contains many sessions, and I will show you one by one. And it's very easy to parse in case you want to do your post-processing by your own. So the file is basically divided in sessions. Every session starts with a begin command here, which is an asterisk here as the first character. Then you have comments. Of course, you can skip them. And after the comments, you have the session data. Okay. Now we will do a small example, and I will show you how it works. Okay. So what we are going to simulate is what we have here in Midas Gen. Okay, let me do a quick test. I want to move to another computer because here we are having some kind of delay with the Chrome remote desktop. Just give me 1 minute. I will move to another computer. Just a second. I will stop sharing and start sharing again. Okay, here we are. Just moved to another computer. Can you hear me well? Okay. I will start sharing my screen right now. Okay, here we are. Okay, so as I told you, we are going to compare our result with what we have in Midas Gen. This is a very simple example. Okay, so a simple structure, 1 bay, 2 floors. Okay, very easy. Everything is linear elastic, and we have rigid diaphragm here. So let's see first of all what Midas Gen says about this kind of structure. So it is a concrete structure, very simple. Okay. So if we run the analysis, first of all, Midas Gen will give me the so-called vibration mode shape result table. Okay, so this is the typical output that you have in any kind of software. So you have an output for all the frequencies that you have, one for each mode, periods, and so on. Then you have the modal participation masses and the modal participation factors. Okay. So let's see how this can be done now in STKO and OpenSees. So if I open up STKO, and of course you will find all the webinars, all the 5 webinars for this file. Okay, so here you have the Midas Gen files if you want to do your own comparison. Now we are going to compare with the Midas Gen frame model, which is basically this one, a frame model where the rigid diaphragm are used as usual, so as a constraint. I will show you that results will change if we use rigid diaphragm or if we use the rigid diaphragm with a different approach. I will show you this kind of feature. That's why I have Midas Gen frame, Midas Gen truss. Okay, and then we're going to compare it with OpenSees frame. Okay, so this is our model. Okay, so same properties. This is very simple. Elastic cross sections. Okay, then we have also elastic shear for account for shear deformability, so that the comparison with Midas Gen is fair. Okay, so you know how to include it. You can use a section plus a shear in axial material, then you put everything together in a section aggregator, and then you have the beam section property. Okay. Now, of course, in this case, this is elastic. You don't need to do this kind of approach, but I wanted to show you the outputs in terms of forces later on. Okay, and then I use a force beam column. The constraints are very easy here. So if I go on condition, you will see that we have fixity on the base. So the base is fixed for all the degrees of freedom. Then, of course, we have the master nodes for every floor. And as you know, the master nodes needs to be fixed in the out of plane degree of freedom because they do not enter the rigid diaphragm interaction. Okay. So we also have here this one. Then we have the rigid diaphragm multi-point constraint. Perpendicular direction is the third one, so the global Z axis. And then we have some nodal masses. Now, if you remember, in STKO, in our forum, we put a TCL script to compute the modal properties, and there was a limitation. It was working only for nodal masses. Now, with this new procedure, you can use both nodal masses and distributed masses. There is no restriction on that, okay? Now, in this example, for the sake of simplicity, I will use nodal masses. But also distributed masses will give you complete exact results. Okay, and then what I do is to create a recorder, as usual, because I want to record displacement and rotations, the modes of vibration, and then some output for section forces when we will run the response spectrum analysis. Then, of course, as usual, you always have to add boundary conditions. Okay, so the 2 single point constraint for the base node and for the master, and the rigid diaphragm, as usual. Then once you are here, most people typically just run the eigen analysis. Now, that is fine, but you have to keep in mind something. When you use the eigen command, you must choose the number of eigenvalues. And in Midas Gen, we decided to use 7 eigenvalues, and also here we have 7. At most, you can choose the kind of solver that you want. Now, by default, you have the Gen band RPAC, or you can change it. I will show you what are the differences, but I will suggest you to use always the default one, which is the RPAC. Now, what is the difference between the RPAC and the full Gen LAPAC? Now, basically, you have 3 options. The default one, which is the band RPAC. Then you have the symmetric band LAPAC. Now, forget about this one because you need a symmetric matrix. So as far as you're using nodal masses is fine. But if you use consistent mass matrices, for example, with the displacement-based beam column or with the solid elements, the mass matrix is not diagonal anymore. So even if they're written symmetric, they actually meant diagonal. Okay, there is a typo in the name of the solver. But if the matrix is not diagonal, the sim band LAPACK is not working. So basically, you have two choices: the band RPAC or the full gen LAPACK. Now, what is the difference? The first difference is that the full gen LAPACK works with dense matrices. So this is already a limitation, because if your model is small, that's fine. But if you have a large model, of course, you will run out of memory if you try to use a dense solver. Then there is another difference, the algorithm that they use. The full gen LAPACK try to extract all the eigenvalues. So once again, when you're doing a small model, the full gen LAPACK is fine, because it tries to extract all the eigenvalues. And then, of course, if I request only 7, OpenSys will give me only the first 7 eigenvalues. But in any way, he will try to extract all the eigenvalues. So it will take time if the model is very large. Instead, the band RPAC uses the RPAC algorithm that instead extracts only the eigenvalues that you are requesting. So plus it works with sparse matrices. So basically, let's say that it is the default choice that you should use. There is only one case in which the RPAC is going to fail, and I will show you just now when it can fail. If I choose gen band RPAC, and let's say I want to use 8 eigenvalues. Okay, now just for the moment, let me comment out the modal properties. I will show you later in a while how it works. I just want to focus on the eigenvalue command, just to show you what are the possible errors that you may encounter. Just going to comment them, so that now we only have the eigenanalysis. Let me try to run this one. And it says, when you find this kind of error with the RPAC solver, error with SAU, this one is the name of the routine of the RPAC library. This one basically means that you are trying to extract a too large number of eigenvalues. Why? Even if the structure has, first of all, there is an introduction that should be done. How many eigenvalues can you request in a model? Basically, you can request a number of eigenvalues, which is at most equal to the number of degrees of freedom with an associated mass. Okay. Now, in this case, we have 8 eigenvalues. The problem is that the RPAC solver, which is very optimized for sparse matrices and so on, it has a limitation. You cannot ask all the eigenvalues. At most, you can ask n minus 1 eigenvalues, where n is the maximum number of eigenvalues available. So this is the only case in which the RPAC solver may fail. But the point is, you may need all the eigenvalues of a structure only if you are doing a very small benchmark. In the general case, your model is very large. You have a lot of degrees of freedom with masses. And so you never need all the eigenvalues, okay? So keep in mind, if you have this kind of error, it's because you're using too many, you're asking for too many eigenvalues. Okay, so now let's go back. This is the only thing I wanted to show you. Oh, there is already a question. Okay. If you have measuring field frames, how did eigenvalue analysis consider the fact that measuring field walls are compression-only elements if you model them as diagonal struts? Should they account for any special consideration in those cases? Yes. Yes, because when you do an eigenvalue analysis, the eigenvalue analysis asks for it uses the tangent stiffness. So in theory, it should take into account the fact that one of them has a positive, goes positive, and it has a 0 stiffness. The problem is that this is kind of strange. I will show you later on what happens when you do an eigenvalue analysis during a nonlinear analysis. The problem is that if you do this analysis at the beginning, okay, there is no displacement in the model. So the initial stiffness of your compression-only element at a displacement equal to 0 will be equal to the full stiffness, okay? So for an eigenvalue analysis done at the beginning, you will always have full stiffness. So in your case, you should consider only one of them, okay? Only one of the 2 trusses. If instead you do the eigenvalue analysis
on a later stage of your model, let's say you push a little bit your model, one of the trusses goes in tension, so it has a 0 tangent stiffness. And if you do the eigenvalue analysis at that point, then it will correctly take into account only the compression, or only the stiffness of the compression truss, okay? But this is a kind of complicated topic. I will give you an introduction of this one, at the end of this webinar, okay? So at the moment, if you want to make sure that everything is correct, assume that your model is elastic. So in your case, when you have 2 trusses, just model one of them. Okay, so if I run the eigenvalue analysis here, it should be fine with 7 eigenvalues. That's fine. So this is the output that you have now with OpenSees. At most, you have the number of eigenvalues that you want. But you don't have anything for the modal properties. So this is the new command that we implemented in OpenSees. So the first step towards a response spectrum analysis, which is the modal properties. Now, the modal properties has no mandatory parameters. All these parameters are optional, okay? The point is that if you only call modal properties, the modal properties will be stored inside the OpenSees source code, the OpenSees memory, and they will be available for response spectrum analysis, but you will not be able to see them. So you have 3 options here. The first one, print, means print the output of the modal properties on the console, so on the screen, okay? If you want them to be printed on the screen. Additionally, you may want to store all these properties into a file, okay? And in this case, you can use the file option. And if you use the file option, the next keyword should be the name of the file, okay? So if you write it like this, it will be a relative path. So in my case, it will write this file inside the folder where I'm running OpenSees. So in this case, it will be this one, okay? Otherwise, you can specify an absolute path. Then you have another option, which is unorm. Why you may need this option? You know that, let me go to the, here to the explanation. And this is a summary of what is contained in the modal properties. So the typical modal properties that we compute is the generalized masses, which is this product. So the eigenvector transpose times mass matrix times the eigenvector, okay, for every mode. And this one will give me a diagonal matrix due to the orthogonality condition between the eigenvectors. And if the eigenvectors are normalized with respect to the mass matrix, this generalized mass matrix will be the identity. If they are normalized in any other way, this mass matrix will not be the identity. Now, how do you decide the normalization of the eigenvectors? You can't, because in OpenSees, the normalization is decided by the solver that you use in the eigenvalue analysis. If you use the RPAC, the eigenvectors will be normalized with respect to the mass matrix. Okay, so in such a way that this product here will give me an identity matrix. If you use the full gen LAPAC, which is this one, they will be normalized by the max. Well, actually, it turns out that they are normalized to the maximum displacement or rotation based on how if they excite more translational mass or rotational mass. So in either case, none of them can be considered as normalized to the displacement vector, which means it will be normalized to the maximum value of the eigenvector. Now, this is not so important because, let me go back to the RPAC. This is not so important because, as you can see, all the other properties, I mean, the only property that change with respect to the normalization of the eigenvector is the modal participation factor, okay? But the modal participation masses, they do not change because in any case, they will be multiplied by the generalized mass matrix. So the normalization here cancels out, okay? And also when you do the response spectrum analysis, the normalization does not have any importance, okay? But in any case, there are cases in which you may need the modal participation factors to be displacement normalized. If you want that, there is an option here. You can use the unorm, okay? So basically, if you use the unorm here, OpenSees use whatever kind of normalization it wants for the eigenvectors, but our routine for the modal properties will normalize the eigenvectors with respect to the maximum displacement component. okay? So this is all about the modal properties, and let's see what it does, okay? Now, of course, you will see that by the end of this webinar, I will show you that in the new version, you will not need to write this command like this, like a plain TCL file. We will have a wizard that will allow you to do everything in a single graphic environment. But this is just to explain you how the command works in OpenSys. So now that I'm using the modal properties command, let's try to run this analysis. And as you can see now, I have the exact output I did before, so basically nothing, the eigenvalue analysis. And then I'm using the domain modal properties. Okay, so this is a small introduction just for the first time you use this command. Then since I've used the print command, it will print everything here on the screen. And the same output is also available in the modal report file that I specified here with the file option. Okay, so this is how the report file looks like. You have many sessions. Okay, at the beginning of a session, as I told you, here and here, to explain you the format of the file, is made of command lines. Okay, so the lines where the first character is an hash is just a command. So if you want to parse this file, it's very easy because you can just skip them. If the first character of a line is an asterisk like this, it means the beginning of a session. And then based on the number, you can understand what session it is. For example, number 2, you have the eigenvalue analysis. Here you have the domain size, for example, if it is a 2D problem or a 3D problem. Then you have the total masses of the structure, okay? Total masses for each degree of freedom. Now, in this case, we are in 3D, so we have at most 6 degrees of freedom. And this is the total masses of my structure. You have now the translational masses and also the rotational masses given by, as you know, if you have seen our previous TCL implementation, if you don't have any rotational masses directly applied on the model, you will not see any rotational mass here. But you know very well that even if you use translational masses with commercial software, you see some kind of rotational participation mass, because basically the rotational mass of a structure is the sum of the direct rotational masses given by the user plus the rotational mass given by the translational masses rotating about the center of mass of the structure. Okay, so that's why many software have rotational masses here, even if you don't input them. Okay, so that's why here you have the total mass of the structure. And this one is the total mass, including the masses at the fixed degrees of freedom. And this one is the total free mass of the structure. Now, in this case, it is equal because I just used masses in the free nodes. But imagine if I'm using distributed masses, okay? Half of the mass of the columns will be fixed at the bottom. So there will be a difference between the total free mass and the total mass. Let me go back here. And we use the total free mass to compute the center of mass and to compute the percentage that you have here of the modal participation mass ratios. Why do we use the free mass? Because sometimes some software use the total mass, but if a lot of the total mass is fixed, your percentage will never reach 100%, because of course you can never excite the masses into a fixed degree of freedom. Okay, so that's why you have this difference. So total mass of the structure, free mass of the structure, center of mass. Then you have the modal participation factor, 1 for each mode and for each degree of freedom. Then you have the modal participation masses for each node, okay, in absolute values. The cumulative masses, okay, once again in absolute values. And then you have the same, so the participation masses and the cumulative participation masses as ratios, okay? So, which is basically this one divided by the total free mass. And this one is basically what you need, just the last one, to understand if your structure in a certain mode has excited a sufficient amount of mass. Okay, now let's go back to the theory of this one. So you know what is a generalized mass matrix. You know what is a modal participation factor. Now, in many softwares, sometimes they don't give you anything about the rotational masses, because it is not so important actually, because what you need is the translational mass. But sometimes you want to know what is the amount of excited mass in the rotational in plane direction, so rotation about the z-axis. Now, the way you can compute this one, since it is not mandatory, some software does it differently. And in many books, if you look about the theory, you see that this vector here is just a vectors of 1 and zeros. 1 in the degree of freedom that you want to excite in that example, and 0 in the others. The problem is that if you use that kind of vector, you will never consider the coupling between the translational masses given by the distance from the center of mass. Okay. Well, in this case, we use a more generalized approach, which is basically the product of these coupling matrices, where you have the diagonal matrices, you have the unity, and in the out of diagonal entries, you have the distances of every node from the center of mass. That's why we need to compute the center of mass. Okay. Now, if you do this, you can also compute the effect of the translational masses rotating about the center of mass. Okay. And then finally, you have the modal participation masses given by this equation. So the square of the modal participation factors times the generalized mass matrix. Okay. Now, what I want to show you in a first stage is just about the rotational masses, because this is kind of strange. Some software do not compute it. Some software compute it, but in different ways. As I told you here, we use the definition, the same one defined by Abacus. So the distances from the node position to the center of mass, but the total center of mass of the structure. Okay. Now, some softwares don't do it at all. Okay. So you don't see any rotational masses. Some softwares like Midas Gen do it, but floor by floor. Okay. So if I run this model, you will see some differences between the output of Midas Gen and the output of OpenSeas. So let me see what is the output of Midas Gen here, and let's compare it with the one given by OpenSeas. Okay, so first of all, the periods are the same. Let me go here, periods and periods here. Okay, they are the same perfectly. So if we go back to the total mass here, we don't have the total mass, but it is the same. Midas do not give you any output for the center of mass, but here you can understand that they don't use a global center of mass. They use the center of mass for every floor. Okay, now if we compare just, let's go to the end and we compare the total masses here, you will see that we reach in the X direction, we start by 88%, 0.736 is exactly the same for the first three modes. So it is picked at the first mode here, and then another 11%, 0.363. So it is exactly the same at the fourth node. So we reach almost 100% here. Okay, same for the second translational mode, which is excited mostly at the second mode, and then something more at the fifth mode, and we reach 99% as here. The translational mode in the Z direction is excited at the last mode, and we have the same amount, 94.7214, so it's exactly the same as Midas Gen. And now we will see some difference in the rotational masses. Now, first of all, you can see that the rotational masses around the Z-axis is the same. So it is not excited for the first two modes. It is excited for the third mode, which makes sense because it is the first torsional mode. 90%, 0.41, exactly the same, and then something more at the sixth mode, so that it reaches 100%. Now, the main difference is in the rotation about the X and Y axis. So you may say, okay, but why do I have this kind of differences? Because they are excited at the same location. So for example, the first mode, which is translational about the X axis, is provoking a rotation about the Y-axis. So it makes sense that I have a small excitation here, but in OpenSeas is much in Midas Gen is much smaller. Okay, let me see here. We have a question. I'm wondering if this command is only applicable in linear analysis. If I have a nonlinear analysis, I will tell you at the end of this webinar. I will show you what happens if you do it in nonlinear analysis. Okay, I have an example for this one. Okay, so this is the same as I told you. Rotation about the x and rotation about the y-axis are not the same. So they are excited at the same position. So as you can see here, rotation about the x at the second one, and then here at the fifth one, but the amount is different. So what is this difference? Basically, it turns out that the difference is because Midas Gen is computing the center of masses separately by frame to frame, floor by floor, sorry. Actually, I don't like this approach because it doesn't give a consistent solution. Why? What happens if instead of modeling my rigid diaphragm like this, I model them as rigid trusses? As you know, it should give the same result from a static point of view. So I suppose they should give the same result also from a dynamic point of view, okay? So if instead of modeling the rigid diaphragm using the kinematic constraint, if I model the rigid diaphragm using trusses, and here is the second example, which is basically the same, but here I'm using two stiff trusses, okay, just to make the diaphragm stiff. If I run this analysis and I look at the table, vibration mode shapes are the same. As I told you, this is not changing the solution of the problem because the rotational masses are only computed in post-processing. So it does not change the periods of your model. But as you can see now, the percentage are the same, okay? So 5% here, and then it reaches 51% where it is here. And here it is exactly the same, 51.9633 and 37.2499. Okay, so the difference is that, in my opinion, Midas Gen is splitting the degree of freedom, splitting the center of mass floor by floor, which is not consistent because as soon as you change the way you model the rigid diaphragm, the result changes, okay? So that's why we choose the approach of using just one center of gravity. Okay, so as you can see, the modal participation factors compares pretty well with the others. There is an extra note that I want to show you about the rotational masses, because the way softwares implement this kind of rotational masses is kind of random. Okay? Now, if I do the same model, let me keep this output here. If I do the same model, but instead of using frame elements, I do it with solid elements, okay? So you have, let me say this one, yes. And here in the files, you will see OpenSys solid. If I take this one, and basically this one is the exact same model, but instead of being done with frames, it is done with quadratic cubic solid elements, okay? Of course, you don't have the rigid diaphragm here, so I will compare it with an OpenSys model without rigid diaphragm, just to see what happens to the rotational masses. If I run this model, as you can see also here, even if I don't have rotational degrees of freedom, I still have rotational masses. Why? Because the rotational masses, as I said, is a sum of the rotational masses directly input by the user. And in our case, there is no direct rotational mass, plus the translational mass rotating about the center of mass. But now let's see what happens in software such as Midas. If I open the Midas Giant Solid, okay, same model without rigid diaphragms, but done using solids. Okay, the analysis is already there, so let me just open up the vibration mode shapes. Everything is correct, so as usual, but as you can see, there is nothing in the rotational masses. Why? Because they say, okay, I don't have rotational degrees of freedom, so I don't need them. Okay, now we made it more general, so we decided to include it anyway. Okay, so the way we implemented this kind of modal properties is the most general one that you can find. At least it is consistent when you change your kind of modeling. So it works with any kind of elements, even if they don't have rotational degrees of freedom. As I said, this is not the rotational mass is not important, but a lot of people are asking us why sometimes it does not compare well with another software. It's just because not every software uses the same approach to compute the rotational masses. Okay. Why I said it's just post-processing and you don't really need it, because actually you don't do anything with these rotational masses. You may only need them if when you do the response spectrum, you apply a response spectrum on a rotational degree of freedom, but this is not possible. I mean, when you do response spectrum analysis, you typically apply the earthquake in the X or Y direction, at most in the Z direction if you want to do vertical earthquake, but you never apply a response spectrum in the rotational degree of freedom, okay? I don't know if there is some kind of remote branch of seismic that may use it, but you will never use it, okay? So that's why I'm saying it is not necessary, it's just for post-processing. Okay, so this is how you can compute the modal masses. Now let's see how to do a response spectrum, and let's compare it with OpenSeas, okay? So I will go back to my, I can close this one. I go back in Midas Gen with the frame model. And this time I will compare it with the frame model made with trusses because it's the one that gives us the same modal properties. And I go back here and I open the OpenSeas frame. Okay, so as I said, first step, the eigenanalysis. Second step, the modal properties. The third step is the response spectrum analysis. Now, once again, I forgot to tell you something. When people do an eigenvalue analysis, they typically just use the eigen command without setting any analysis before. This is fine. However, in OpenSeas, when you use an eigen command without specifying a previous analysis, it tries to use the default values. For example, the transformation method for constraint, a full general solver, a linear algorithm, which is everything is fine, but imagine you have a very large model. You cannot assume that you can use a full solver here. You may want a sparse solver, okay? So that's why I typically add an analysis here. Can you please mute the microphone? Sorry. Just a second, I have to mute the microphone. Okay. As I said, sometimes you may need to do a very large analysis. So your model is very large. So you cannot assume that the default of OpenSeas used when you use the eigen command without specifying the analysis is fine. Okay. So typically what I do is before using an eigenvalue analysis, I set up another analysis using just 0 time steps. Okay. This is for, I mean, I don't want to run any analysis before. I just want to set up all the things that I want to be used with the eigen command. So the transformation method, for example, because I don't know what is the default for OpenSeas, I want to use, in this case, the full general, but imagine my model is very large. I want to use another solver, okay? So I don't want to use the default given by OpenSeas because I'm not sure that those defaults are fine for me, okay? So this is just a side note. Okay, so eigen command, modal command, then the last one is the response spectrum. Now with the response spectrum, the kind of command is this one. The command is response spectrum. Then you have to provide the time series tag. The time series is the time series that you want to use as the response spectrum. Then you have to tell in what direction you want to apply it. Now in my case, I want to apply it in the X direction. And optionally, you can use scale. Now the scale is something that I will explain you when I will talk about the nonlinear, when I will talk about using response spectrum with a nonlinear model, okay? So for the moment, don't care about the scale, okay? You just need to provide a time series for the response spectrum and the direction. Okay, so once you have this one, and of course the time series is a path time series with the response spectrum. Once again, I will show you that in the final version, you don't have to input all the files manually. You will have a complete wizard that extracts the response spectrum for you. I will show you later on. Now, if I run this analysis here, the response spectrum will compute the modal displacement for each mode and will store the result. Now, if you have a recorder like this one, he will store the results for every requested component. Now, in this case, displacement, rotation, and section forces, okay? And we store each one of them for each mode. Okay, so let me just run this analysis with also the response spectrum. So as you can see now, we have let's see the output. First the eigenanalysis, then using domain modal properties, then the output, and then here you have using response spectrum analysis developed by blah, blah, blah. Okay. So now if you go in the post processor, you can open the OpenSys frame and PCO file. Okay, so in the PCO file, these are the results that we have: displacement rotation, modes of vibration, and section forces. Now, if I go here, I have one stage and I have 7 steps. Okay, why do I have 7 steps? Because basically the response spectrum will create a step, one step for each mode of vibration to store the modal results. Okay, so they are not combined at this point. I will show you how to combine them in post-processing. So basically now you have the modal responses for each step, and basically it means for each mode. As you can see, the time is not incremented. The time is kept to 0. Okay, so you always have a time 0, but you have the output for the different modes. Now, before looking at this, let's have a look at the modes of vibration. And I use the modes of vibration also for the deformation. Let's deform it a little bit more, even more. Okay, so this is the first mode. And as you can see, the modes are here. So first mode, second mode, third mode, rotation, and so on. Okay, up to the last mode, which is the vertical direction. Perfect. Now let's see the output in terms of displacements. Okay, when you see the output in terms of displacement, and I want to increase them a little bit, and of course not modal vibration, but displacement. Okay, so this is the modal displacement for the first mode. Then for the second mode is not there, of course, because the second mode is along the y direction, but my response spectrum is only along the x direction, so it is not excited. Same thing for the third mode. Then you have something for the fourth mode, because it was the bending about the y-axis, and 0 in all the others. Okay. Now, of course, most softwares do not give you this kind of output. They directly give you the combined output. We decided not to do so because OpenSys is very flexible. It gives you many results. So we cannot know a priori what are the results that you may want to be combined. So we decided to do something different. We store all the results for every mode, and then you can do the combination outside in post-processing. Now, don't worry, because doing you don't have to do the combination manually. We will provide scripts and user interfaces for doing the combination in post-processing. Now, just to do that, I want to show you the new feature that will be available in the new STKO version. I mean, version number 2 that will be available at the beginning of January. So let me close this one. Yes, and of course I'm going to use not this one. Sorry, I have to start the developer version. Give me a second. Okay, let me close this one, because of course this is the current version 1.1.5 that does not have this new feature. Now, if I run the new STKO version, I will show you how you can post-process things in STKO. It is a very flexible feature because in version 2, we implemented the custom Python scripting for post-processing as well. Okay, so now basically the post-processor of STKO is like a MATLAB environment. You can do whatever you want with your results. And one of the applications can be, for example, the combinations of the results. Okay, now if I open the output of the OpenSys frame model, okay, as you can see here, I have all the results that are requested, okay, as before. And if I go here, I can only see, for example, displacements of my 6 modes, but they are not combined. Okay, how do I combine them? In the new feature, you have a new editor here, which is called script. If you open it up, you will find that you have a new window here. Now let me make it a little bit larger so I can show you how it works. This is kind of a MATLAB-like environment. Oops, it's too large now. And it is called script editor. Okay. And basically it is made of a script explorer, pretty much like in MATLAB, where you can decide what are the directories where you have your Python scripts. Okay. Now here, for example, I have some scripts for my post processor. And then down here, you have a script editor, okay, where you can type your script, you can run it, you can save it, you can change it, you can do whatever you want. Now, in my case, I'm using, for this example, a test for the virtual result of response spectrum. Now, what are virtual results? As you can see here, I have just a finite number of results. But what happens if I want to compute a result as a function of the result that I already have in my database? Okay, I can do it like this. So you need to know Python, of course. You need to know the commands given by STKO. And then, for example, here you can say, okay, I want to combine, for the modal combinations, I want to combine displacement and rotations for the nodal responses and section forces for the element responses, okay? Then you can write some code to interact with the user. For example, here I'm using a code to open an input dialog where the user had to choose the modal report file, okay? Then once I do this, I get a reference to the current document, which is this one. I get a database. If there is no database, I will throw an error. So I get the database. Then I can define two functions for doing the modal combination. Now, in this case, I have the CQC. The CQC wants all the modal responses. That this one is a list of results. Now, in my case, it can be a list of displacement for each mode, for example. Then I start them to 0, I do my CQC combination, and then I give you back the square root of this combination. Okay. Now, without going into the details of the CQC, let's say this is a general function for combining the results. Okay. Then here I'm using another small command to parse the modal report file and to get the eigenvalues. And here I will return the eigenvalues from the modal report file. Okay, so I get the eigenvalues. I get the damping factors for each mode in case you want to use different dampings for each mode. Eventually, if you want to switch on and off some eigenmodes, you can scale them. Now, in my case, I don't want to scale any mode, so I use 1 for all of them, and I use the same damping, 5% for all of them. And then I say, okay, for each nodal result requested by the user, get the nodal result name and get from the database the nodal result at the current step, because I said that the step 0 is for the eigenmode 0, the step 2 is for the eigenmode 2, and so on. Now, in my case, I have a list of 7 results, okay? Then I pass this list to the CQC function, and this one will compute a derived result, okay? Now, this derived result, of course, then does not exist in my database, but as you can see, I'm creating in my Python script. Now I can customize it. For example, I can give it a different name. In my case, it will be response spectrum CQC slash the name of the original result. Then I can set the labels for each component if I want, and then I add it back to my document. Okay, and I do the same for the element result. Okay. Now, don't worry if you don't know Python, because all these scripts will be the new version will be available in a user interface, in a wizard, so you don't have to write the scripts. But for those of you who like developing codes and doing their own stuff, keep in mind that with the Python extension of the post processor, you can do whatever you want with our post processor now. So you're not limited to visualize the results given by OpenSys. You can actually customize them. So now if I run this one, you will see that some new result will appear here, okay? 2 new results for the nodal results and 1 result for the element result, okay? So let's run the script. Now, as I told you before, it is asking me for selecting the modal report file, which is this one. Open it. And then the script is done now. As you can see now I have, let me close this one. I have displacement, response spectrum CQC, rotation, response spectrum CQC, and section force, response spectrum CQC. Okay, now let's see how it looks like. I have displacement here, and this is the standard displacement. And instead, and as you can see, this displacement is changing step by step, okay? Because basically this one depends on the step. If I select the combined displacement, now it is pretty similar to the first one because this structure is almost completely excited in the X direction. But as you can see now, it is constant for every mode just because it is already combined. So it does not depend on the mode anymore. Now let's see what happens with the internal forces. Of course, in the new version, now you have the beam diagram. Okay. Now, if I look at the section forces and I look at the moments about the Y or no Z axis, or actually no, the Y axis, but the first mode. Okay. Now, as you can see, I have positive and negative moments. This is fine for every mode. Okay. So before the combination, they have their own sign. Okay. They are combined. Perfect. Now, when I do my modal combination, as you can see, the only point is that they lose the sign, and this is completely fine. Let me reduce it a little bit. 5. And as you can see now, you have the results for your combined modal results. So basically, as I told you, this is the reason why we did not include the modal combination inside OpenSees, because now you can combine whatever you want in post-processing. And this is way more flexible because many softwares only give you the response spectrum results in terms of displacement rotations and section forces. But imagine you want to compute drifts, for example. You cannot compute drifts on an already combined displacement field because they lose the sign. So you cannot compute the drift from that. Instead, in this way, since you have all the displacement for every mode, you can compute the drift for every mode and then do the CQC combination on the drifts, for example. So of course, there is more freedom. As I said, don't worry about the Python scripting because I know that not all of you is expert in Python. And of course, we will provide a user interface for doing the standard combinations, okay? So I just wanted this occasion to show you what is the great new features of STKO in version 2.0, okay? And of course, you can do many more things with this kind of post-processing. Now, before concluding, I wanted to show you what happened because someone was asking me what happens if I use this procedure in a nonlinear environment. I prepared a small example here, which is test nonlinear. It's a very small test. Because typically this is kind of very nice because in OpenSees you can apply the eigenvalue analysis wherever you want. So let me close this one because I don't need it anymore. And I reopen the standard STKO. And I just want to show you what is the effect of using the eigenvalue analysis, not in the elastic case, okay, when you have nonlinear materials. Now, if I go in test nonlinear, this is a very simple column, okay? You have a fix at the base. So this is basically a simple cantilever. And I'm just using a simple mass applied here on the top in the 3 directions. I'm asking just for a single mode, okay? And this is quite interesting because I'm using a certain vertical load that makes my my structure go a little bit into a nonlinear stage, okay? So how did I set up this thing? First, I have a recorder, then I have a constraint. As I said, I have a dummy analysis just to set up a sparse solver and all this stuff, but I'm doing 0 steps, okay? Duration 0, just to set up the analysis before the first eigenvalue. So basically, this first eigenvalue here analysis, just one mode, and the associated modal properties. They will give me the modal properties for my elastic model, okay? Then after this, I run a vertical analysis, applying this vertical load. And then I do once again another eigenvalue analysis, still just one eigenmode. But what is going to happen is that this eigenvalue here will consider the tangent stiffness as the previous one. Also, the previous one was considering the tangent stiffness. But at the beginning, the tangent stiffness is also the initial stiffness matrix, okay? Now, in this case, the tangent will be the tangent one, the actual tangent. So I would expect my period to increase from the first one to the second one, okay? Then here I was applying horizontal load and I was doing a horizontal analysis, but I just removed them because I don't need them, okay? So if I run this analysis, let's see what happens. Now, of course, here I don't have any rotational mass because there is no distance from the center of mass. Let's go at the very beginning. Okay, so first eigenmode, the period is 0.306, okay? First period, 0.306. Then if I go, I run the first vertical analysis, then the second analysis, 0.37. So as you can see, the period has increased, okay? So I don't want to tell you that you can use the eigenvalue analysis in a general nonlinear analysis because we are studying this kind of stuff right now because it is not so easy. I mean, they use the tangent stiffness, but the problem is that you have to make sure that the tangent stiffness makes sense in that kind of problem. Because here I'm just, if you look at the output of this one, that's nonlinear. If I look at the output of this one at the end of my step and I look at the stresses, section fiber stress, and I switch off the stresses of steel, I can see that my minimum stress is minus 18. And my material model for concrete has a peak stress of 13. So if I run my test now here, 18 is about here. So as you can see, it's a very small nonlinearity, okay? The problem is that what happens if your tangent stiffness is about here? It will be 0. So you cannot compute the eigenvalues around here. Or even worse, what happens if it sends you in a nonlinear stage where you have negative stiffnesses? You're going to have, you cannot compute negative, then you will have negative eigenvalues, but then it will give you a problem when you compute modal properties because you have to take the square roots of the negative eigenvalues, and it is not possible. So the point is that you have to understand what it means to use the tangent stiffness. We are working on it. The problem is that, in my opinion, the tangent stiffness is fine as far as your nonlinearity is very small, because the tangent stiffness is very close to the secant stiffness, okay? Imagine I'm here. Let me do just a small annotation. I was at 18, so basically here. Now my tangent stiffness is this one in my case. And the secant one is this one. Now it is impossible to run a line here. Yes, line. Oh, let me do it again. I'm 18. And this one is the tangent stiffness, more or less. And the secant one is here. So as you can see, the secant and the tangent are pretty much the same. So it is fine. But what happens if I am here on the peak? Now imagine this is my concrete curve is going down. What happens if I am here? The tangent will be flat, but the secant will be this one. So it is not the same. Even worse, if I am here, the tangent will be negative. So actually now we are trying to understand what happens to open Cs when you try to apply the eigenvalue analysis very later on in a very strong nonlinear point. So it is feasible now, but pay attention when you do it, okay? Don't do it without carefully looking at the result. So this is as far as the modal properties are concerned. Now for the response spectrum, you need to do something different, because if you do a response spectrum on a nonlinear model, okay, even if you apply the eigenvalue analysis at the beginning, it will compute a modal displacement, assuming that the model is linear because I'm using the eigenvalue at the beginning, okay? The problem is that if I apply, as I'm doing in the response spectrum, the total displacement, the total modal displacement in my model, and my model is nonlinear, it may happen that it will not behave linearly, but it will give me the forces associated to a nonlinear behavior of my structure. And this is not correct, okay? Because I'm computing a displacement. Oh, let me share my screen again. Okay, this will be not correct because I will compute the modal displacement using a linear assumption, but then I will compute the forces from my modal displacement using the real nonlinear model here, and this is not fine because the two things will not be consistent. Okay, so that's why in the modal properties, let me go back to my previous example. OpenSys frame. That's why here in the response spectrum, I have the scale factor. So this scale factor can be used to scale the output displacement of the modal properties. So you may say, why do I need to do this one? Okay, now let's imagine my model, in this case is linear, but imagine my model was non-linear because I had to do, I don't know, after the response spectrum, I had to do a pushover analysis, and I don't want to compute two different models. Okay, I want to use the same one with fiber section, nonlinear material models. So I do the eigenvalues at the beginning, and I will compute the modal displacement assuming the initial stiffness of my model. Okay, now let me do a small drawing. Okay, here. So X and Y. And this is the behavior of my structure in nonlinear with a nonlinear displacement. Okay, of course I don't know it, but at the beginning I compute the initial stiffness and I do the eigenvalues at the beginning. Okay, from this eigenvalue, my response spectrum will compute a certain displacement, which is, let's say, here. So this one will be my modal displacement using the assumption of the initial stiffness, which is this one. So actually I would expect the output being this force, assuming a linear behavior. The problem is that when I plug this displacement inside OpenSys and I ask for the results in terms of forces, OpenSys will give me the nonlinear force, or even worse, it may not converge if this displacement is too large. Okay, so how do I obtain this kind of elastic force? This is the reason why I'm using the scale factor. Imagine that this is the total displacement computed by the response spectrum. I scale it by a small factor, let's say 1 to the power of -3. Okay, -3. So I have this displacement here, U modal tilde. Okay, a small one, a small displacement. This will give me an almost elastic stress, which is here. Okay, now of course you cannot see it, but if you do a zoom of this one, I will have my nonlinear curve, my very small displacement here, and my elastic stress, which will be this one. So it is not elastic, but very close to the elastic one. Then in post-processing, in STKO, before doing the combination, you can post-multiply the stresses by the inverse of the scale factor that you applied here. So if I multiply this one by that scale factor, it will give me back the elastic stress, okay? So this is still a work in progress. We are working on it. So just to answer to the two participants that asked for what happens if I do an eigenvalue analysis in a nonlinear environment, do it with care because it can be inconsistent. So we are working on it. You can do it, but do it carefully, okay? Because actually the eigenvalue analysis is not something that should be done in a nonlinear environment. Same thing as a response spectrum. So we need to study about this one. Okay. So I think we have, and this code is going to be in OpenSys. As I told you, do not expect to see it tomorrow because the code is ready. We are sending it to the OpenSys code maintainers. It will take some weeks for them to include it in their source code. And after that, you have to wait for them to compile a new version of OpenSys, okay? So it will take a little bit when it will be ready. That's why I wrote here part one, okay? Because actually, when everything will be available in OpenSeas, and when after January we will have version 2 of STKO, you will see that in the new version, the response spectrum analysis will be already implemented by OpenSeas, and we will have many more features for doing the response spectrum without any need to know Python scripting. I just want to give you a brief preview of what we are developing now. This is just a video. This is a small example on how to create the response spectrum. Actually, before I did the response spectrum manually using the path command. But as you can see, when we have this kind of Python environment, we can customize everything. And here, in this case, we have the definition for the response spectra. As you can see, we have implemented many codes. In this case, we're using the Italian one, NTC. Then, in this case, he's going to change to other codes. And then you can use the national code. It's much easier rather than going and inputting the file. So you don't need any support file. They can be, if I record properly, they can be obtained also from the internet. And then there are many other new features. Let me see. As you can see, you can change them. You can see the output in terms of spectral acceleration, velocity, displacement. Let me see. Okay, Eurocode. And the hash, and then we have also the user one. Of course, if you want to do your own list of periods and values, you can take them from an Excel spreadsheet. And we also have another interesting feature that if you don't want to use a designed code response spectrum, let me see, what is it? You can pick it from file, and you can also use a real spectra. I think this one was the example. Here it is. Okay, and then we compute all the derived results. So there are many things that can be done with this kind of Python environment. So as you can see here, you will have a user interface for defining the response spectrum, for defining the input for the response spectrum analysis. So you don't need to do an eigenvalue, then manually write the code for the modal properties, then a manual code for the response spectrum. Actually, now everything will be available in a single wizard. Same for the output. Okay, so you will not need to do the combination manually as I did. Okay, this was just an example to show how powerful will be the post-processor STKO in the new version. Okay, so I hope you enjoyed it, and if you have any question, we have some minutes here. Thank you, Nicola. Why did you get the warning unsupported attribute? Actually, okay, let me show you. That is not an error. It's just a warning because at the beginning, I was storing the eigenvalues inside the MPCO recorder. But since I don't need them anymore because we are using the report file, okay, I just need to remove that error. Okay, in the new version, you will not see that warning anymore. Okay, because now the eigenvalues are not stored inside the MPCO recorder, but are stored inside the modal properties report file. Okay, so don't care about that warning. In the new version, it will disappear. Okay. As usual, the video will be on our YouTube channel, and by tomorrow I will send all these input file on our website. But as I told you, you have to wait for the new STKO version and the new OpenSys version to be able to run them. Okay. We have another question for Sigma 1, is there any way to know the default analysis component number for the eigenanalysis? Yes, and the only way you have is to go into the source code. So let me show you how it works. The only way you have is to look at the source code. If I share my screen, is it share screen? The only way you have is to go into the source code, open OpenSees, and you have to look for the eigen command, okay? So if you don't know how to navigate inside OpenSees and you want to find the eigen command, you can just type here eigen, like this, and then search all. You will find many of them. If you're using OpenSees STKO, you need to go under the TCL report, and then you go here. Here you have the eigen command, and when they find the eigen command, they run the eigen analysis. You go here. Let me go here in the source code. You go here, and then you go here. As you can see in the eigen analysis, they are parsing something, and then at a certain point, they say, okay, if there is a static analysis, I create a static model. That, for example, if there is no test command, I will create a normal balance command with those default values, 1 to the -6 as a tolerance and 25 iterations. If there is no algorithm, I will use the Newton-Raphson. If there is no constraint handler, I will create the transformation. If there is no number, I will use the RCM. And then, and this is the most important thing, if there is no solver, I will use the profile SPD. Now, what happens with the profile SPD? The profile SPD only works with some kind of matrices, which actually they are fine. If you do an eigenvalue analysis, you are supposed to use a linear model. If you use a linear model, a profile SPD is fine. But if your model is very large, probably it's not the best one because you need to use a sparse matrix. The problem is that if you want to do the eigenvalue analysis when your model is not completely linear because it is undergoing a nonlinear stage, probably your model, your system metric will not be SPD, which is symmetric and positive definite. So that's why typically you can trust the default values, but sometimes they may not work. Another example is the transformation handler. As I told you in a previous webinar, if you have a very complex model and you have many overlapping constraints, it may happen that the transformation metric is not going to work. So in my case, I typically use the penalty method. That's why I always prefer to define an initial dummy analysis, set up all the components that I want, that I know they will work in my case, and then I run the eigenanalysis, okay? So otherwise you can use the default one. The problem is that you have to trust them. Okay? And if you don't know, I mean, if you can go out, you can look at the source code. The problem is that you need to know how to look at the source code, okay? Is there any other question? I think we have other 5 minutes. Okay, I think we are done. And okay, so see you in the next webinar. So thank you everyone for taking part to this webinar.